We have rows and columns, and the rows are for the variable x, y, and y prime for x squared plus y squared minus 1. Now we draw short line segments with these slopes at these points. The result is the direction field shown in figure 5. See figure 5. Part B. We start at the origin and move to the right in the direction of the line segment, which has slope -1. We continue to draw the solution curve so that it moves parallel to the nearby line segments. The resulting solution curve is shown in figure 6. Returning to the origin, we draw the solution curve to the left as well. See figure 6. Back to the text. The more line segments we draw in a direction field, the clearer the picture becomes. Of course, it's tedious to compute slopes and draw line segments for a huge number of points by hand, but computers are well suited for this task. Figure 7 shows a more detailed computer-drawn direction field for the differential equation in example 1. It enables us to draw with reasonable accuracy the solution curves with y-intercepts -2, -1, 0, 1, and 2. See figure 7. Back to the text. Now let's see how direction fields give insight into physical situations. Simple electric circuit shown in figure 8 contains an electromotive force, usually a battery or generator, that produces a voltage of big E of t volts, big V, and a current of big I of t amperes, big A, at time t. The circuit also contains a resistor with a resistance of big R ohms, and the symbol for ohms, and an inductor with an inductance of big L henries, big H. Ohm's law gives the drop in voltage due to the resistor as big R, big I. The voltage drop due to the inductor is big L of the derivative of big I with respect to t. One of Kirchhoff's laws says that the sum of the voltage drops is equal to the supplied voltage, big E of t. Thus we have big L times the derivative of big I with respect to t plus big R, big I equals big E of t, which is a first order differential equation that models the current big I at time t. Example 2. Suppose that in the sample circuit of figure 8, resistance is 12 ohms. The inductance is 4 henries. And a battery gives a constant voltage of 60 volts. Draw a direction field for equation 1 with these values. Part B, what can you say about the limiting value of the current? Part C, identify any equilibrium solutions. Part D, if the switch is closed when t equals 0, so the current starts with big I of 0 equals 0, or use the direction field to sketch the solution curve. See figure 8. We have a switch, we have big E, big R, and big L. Solution, part A. If we put big L equal to 4, big R equal to 12, and big E of t equal to 60, in equation 1, we get 4 times the derivative of big I with respect to t plus 12 big I equals 60, or the derivative of big I with respect to t equals 15 minus 3 big I. The direction field for this differential equation is shown in figure 9. See figure 9. Part B. It appears from the direction field that all solutions approach the value 5 big A, that is the limit as big I of t, the limit as t approaches infinity of big I of t equals 5. Part C. It appears that the constant function big I of t equals 5 is an equilibrium solution. Indeed, we can verify this directly from the differential equation. The derivative of big I with respect to t equals 15 minus 3 big I. If big I of t equals 5, then the left side is the derivative of big I with respect to t equals 0, and the right side is 15 minus 3 open 5 close equals 0. Part D. We use the direction field to sketch the solution curve that passes through the point 0, 0, as shown in figure 10. See figure 10. Notice from figure 9 that the line segments along any horizontal line are parallel. That is because the independent variable t does not occur on the right side of the equation. Big I prime equals 15 minus 3 big I. In general, a differential equation of the form y prime equals f of y, in which the independent variable is missing from the right side, is called autonomous. For such an equation, the slopes corresponding to two different points with the same y-coordinate must be equal. This means that if we know one solution to an autonomous differential equation, then we can obtain indefinitely many others just by shifting the graph of the known solution to the right or left. In figure 10, we have shown the solutions that result from shifting the solution curve of example 2, 1, and 2 time units, namely seconds, to the right. They correspond to closing the switch when t equals 1 or t equals 2.